Okay, so this is Math 335 at SUNYGeneseo, and we, having studied incidence geometries, are getting ready to look at neutral geometry. Now, neutral geometry is called neutral because it doesn't give a rip about Euclid's parallel postulate. Now, you'll remember that Euclid's parallel postulate said, okay, I've got a line, I've got a point not on the line. How many lines through this point P can be drawn parallel to that line L? And Euclid's answer was 1. Of course there's 1. How could there be any more than 1? And it turns out that there are many ways where that could be more than 1. And because of that, we have this thing called neutral geometry. Neutral meaning that it does not care about Euclid's parallel postulate. So the glory of that is that if we can prove something in neutral geometry, then it will be true whether Euclid's parallel postulate is true or not. Whether the answer to this question is one parallel line or whether there are many parallel lines, oh, we don't even want to think about that yet, or whether there are no parallel lines. That's right, all lines have to cross. But there are some theorems that are true regardless of where we do them, and those are what we call neutral geometry. So we're going to build a neutral geometry in the way you would expect us to build a neutral geometry. We're going to start with some undefined terms. There are 6 undefined terms that we will take on. Some of them should be very familiar to you. The idea of undefined terms being point and line. Points will normally be represented like so. Lines will normally be represented like so. We're going to take half plane as an undefined term. We generally look at a plane as a sort of a two-dimensional, goes on forever in all directions, flat as a table, on and on forever and ever. We think about it that way, but that's because we think Euclidean. In Euclidean geometry, things are flat. Things are not necessarily flat. So we're going to take half plane as an undefined term. There are 2 intriguing undefined terms to me. The idea of distance and the idea of angle measure. These are slight nods to Birkhoff from 1932. He created an axiomatic system for geometry that was beautiful because it involved measurement. We give a slight nod to him in this regard because if we can bring in distance and angle measure as undefined terms, then we can bring in a lot of our algebra and properties from the real numbers to help the geometry along. We're going to end up only using 6 axioms. 6 is more than Euclid had. It's not as many as Hilbert had. It's not as many as the School Mathematics Study Group from the 1960s had. And some of those SMSG postulates are redundant. We're going to have 6 pretty much not redundant axioms, 6 independent axioms to build our neutral geometry. So here's axiom 1, and this shouldn't surprise anybody. The collection of all points forms a non-empty set. There is more than one point in that set. Let's ask the question. Why do we need to say that? Why do we need to say that there's more than one point in that set? Think about, as we go on, think about what would happen if there was only one point, or if there were no points at all. If there are no points at all, then your geometry is really easy to work with because there just aren't lines. So you don't have to worry about them crossing because there aren't any. We should think about that. Axiom 2. Every line is a set of points. For every pair of distinct points A and B, there is exactly one line L such that A is on L and B is on L. Quick nod here. This is a nod to set theory. We're going to use set notation to deal with points and lines and points being on lines. We're going to say things like A is an element of L and B is an element of L, and that's going to get away from having to say that on is an undefined term. We can use set language to get around that a little bit. So every line is a set of points, and this is a familiar incidence axiom. For every pair of distinct points, A and B, there is exactly one line L such that A is on L and B is on L. This should sound familiar to you. It is an incidence axiom that we have talked about. Quick little side note here. It's a cute little side note. If L is not equal to M and L is not parallel to M, then there exists exactly one point P such that P is on L and P is on M. So if I have two lines and they're not the same and they're not parallel, then there is exactly one point on both of them. This is another one of those things that should sound familiar. It flows from incidence geometry. The curious thing about that is that you should be able to prove it at this point, and you should think about how you would prove it at this point using everything we've done with incidence geometry. This leads to a trichotomy, and the trichotomy says either L is M or L is parallel to M, or the cardinality of the set of points in the intersection is 1. That trichotomy holds regardless of the geometry, whether you're using the Euclidean parallel postulate or one of its negations. Given two lines, they are parallel, or they are equal, or they have one point in common. Not going to have a couple of lines with 2 points in common regardless of how you bend the surfaces. Axiom 3. For every pair of points P and Q, there exists a real number PQ called the distance from P to Q. For each line L, there exists a one-to-one correspondence from L to R, such that if P and Q are points on L that correspond to X and Y are real numbers, then PQ is the absolute value of X minus Y. We're going to go back to Math 239 for a moment, Introduction to Proof. One-to-one correspondence. So the one-to-one correspondence means if we have two different y values, two different values in the codomain or in the range, they come from two distinct values in the domain. So if you give me two real numbers, they have to correspond to two different points on L. And if you give me two different points on L, they have to correspond to two different real numbers. Okay? Okay. Let's think about that. One-to-one. The other word big from Math 239, that's the big word from Math 239. Surely your teacher, your professor talked about onto. I wonder if this function is onto. That is to say, given any real number, can you find two distinct points that are that far apart? Interesting. I'll just let that linger. You can bring that to class. We'll probably talk about it. Hey, this gives us, oh, wait, no, not yet. Can't go there. This gives us a chance to talk about betweenness. So I'll talk about betweenness. We get to talk about betweenness at this point because we begin to think about any line as a number line. I mean, that's what this really is. I've got some line right here. I've got P right there and Q right there. So P corresponds to some number X and Q corresponds to some number Y. So the distance between them is the absolute value of X minus Y. It's the difference in their one-dimensional coordinates. So we get to talk about betweenness. We get to say that C is between A and B if A, B, and C are collinear and AC plus CB is AB. That's what we mean when we talk about betweenness. It's one of the things in a high school geometry class that we do really, really early on. We talk about, okay, I've got my line segment AB, and I'm going to put some point C on the line segment. How do I know if C is between A and B? Well, if this is 7 and this is 13 and that's 20, then I have C between A and B. But if those distances were not to add up nicely, I would know either C is not on the line segment or C is not between A and B. I would have to know that. Now this is obvious. This is flat out obvious. There is nothing surprising in this result, but it still has to be built. It still has to be built. By the way, if C is between A and B, this particular textbook uses this notation for C being between A and B. And this notation gives us a way to talk about segments and rays, because we know what segments are. The segments are a segment AB is A and B and all the points between A and B. We can talk about rays. We can say that ray AB is segment AB and then all the points P that are beyond AB on the line. So we would say all the points for which B is between A and P. And those are things to help you think about. Those are things to help you think about this geometry. So far nothing surprising, and that shouldn't be surprising because we're building a geometry with which we are somewhat familiar. By the way, this whole definition helps us talk about congruence. We can talk about congruence because given any 2 points, they lie on a line. And given 2 points that lie on a line, there's a distance between them. And so 2 segments that are congruent have the same distance between the endpoints. Just things to keep in mind. All right, so a theorem for you. If P and Q are 2 points, then first PQ is equal to QP. The distance from P to Q is the same as the distance from Q to P, which seems obvious, but again, things that are obvious but not axioms still should be proven. The distance PQ is greater than or equal to 0, and PQ is 0 if and only if P is Q. So the distance between P and Q is equal to 0 if and only if P and Q are the same point. The first two parts of this are nice consequences of algebra. Algebra comes to the rescue for us. The distance between P and Q is some absolute value of X minus Y. So you should think for a moment, this is PQ, you should think for a moment about what the distance QP is and whether or not those two quantities should be equal. We can talk about that when we come together tomorrow. Number two kind of flows from the fact that we're talking about an absolute value. PQ is a distance. Distance is an absolute value of a difference between two numbers. And so I think that flows fairly easily. The third part of this theorem is an interesting thing. And as with all biconditionals, we're going to go the one way and then the other. So let's go this way first. So if PQ is 0, then the absolute value of x minus y is 0. Well, there's only one way for the absolute value of x minus y to be 0, and that's if x is y, and x corresponds to some point P, and y corresponds to some point Q, and our relationship is 1-to-1, which means that P and Q are uniquely determined. That's the idea behind the one-to-oneness of the relationship. That's where that comes into play, because x is uniquely assigned to point P, and y is uniquely assigned to point Q. Going the other way, we start with P being equal to Q, and things flow very nicely this way. P is uniquely assigned to the point to some number x. Q is uniquely assigned to some number y, and so that kind of flows without too much trouble. Point of order here. Whenever we talk about something that satisfies these three properties, we call it a metric. It's a metric, it's a way to measure things. You are familiar with several metrics. I will share some of them with you. You are familiar with the standard Euclidean metric. The Euclidean metric is the distance formula that you picked up in high school. That is what we commonly think of by the distance between 2 points. Sure enough, if I have 2 points in the coordinate plane, A, B, A and B, and I take the distance from A to B, that is exactly the same as the distance from B to A. If I have 2 points on the coordinate plane and I use standard Euclidean distance, that distance will always be non-negative. And the only way for the distance between 2 points to be 0 would be if those points were the same. There are other metrics that Venema talks about in his book. One is the taxicab metric. In the taxicab metric, you add the absolute values of the differences in the horizontal direction and the vertical direction. It's called taxicab because in the standard Euclidean metric, if I have 2 points, P and Q, the standard Euclidean distance goes this way, but the taxicab distance says, no, in cities, we can only go this way and this way. So we would add, I don't know, 4 plus 3 to get 7 as the taxicab distance. The Euclidean distance on the Euclidean metric would be 5. Okay? Okay. There's a third metric. There's the spherical metric. And in the spherical metric, you have some sphere, and you have 2 points on the sphere. And so you're looking for the distance between them. It is the length of the shorter arc on a great circle between those 2 points. And clearly, if I take that arc from P to Q, that's the same as if I take it from Q to P, and that distance will always be non-negative. And the only way to get that distance to be 0 is if those 2 points are the same. Okay, so when we talk about metrics, I mean, you're thinking distance, but you're not always thinking Euclidean distance. There are other ways to measure distance, and any measuring system that satisfies these metric properties is going to do just fine for us in this geometry. So let's sort of coordinatize the grid. A one-to-one correspondence, call it F, going from L to the real numbers, such that PQ is the absolute value of f of P minus f of Q for all P and Q on the line L, is called a coordinate function for L, and f of P is called the coordinate for P. A coordinate function. So what does that look like? Well, in the Cartesian grid, on the Cartesian metric, if you have some line, the traditional y equals mx plus b, we would call f of xy x times the square root of 1 plus m squared. That is one coordinate function. The 1 plus m squared is somewhat intuitive. I'll leave that dangling on purpose. But if you were to take 2 points P and Q on that line, the distance between them would be the absolute value of the differences of those coordinates. If you have a vertical line, you just let the y coordinate be the coordinate. That's sort of why it's called a coordinate. In the taxicab system, I've got some line. It's the traditional y equals mx plus b. In this case, we would let f of x and y be x times 1 plus the absolute value of m. It serves roughly the same purpose as the other metric. They're coordinate functions, which brings us to the ruler placement postulate. And the ruler placement postulate says, for every distinct P and Q, there is a coordinate function f from the line PQ to the real numbers such that f of P is 0 and f of Q is positive. Now let's talk about what that means and why it's called the ruler placement postulate. Why is that called the ruler placement postulate? Because no matter where I am on this line, I can decide that there's some place that's going to correspond to 0. And maybe the positives go this way, and maybe the positives go this way. It doesn't matter. I can put 0 somewhere. So even if I use one of these weird metrics, if I want to apply it to this line, no big deal. I just say, hey, subtract whatever to make the thing work so that this point P corresponds to 0. If under a particular metric, P would have a coordinate of 5, I just subtract 5 from everybody's coordinates, and that allows me to quote unquote place my ruler so that I have a starting place. I've got 0. This is fairly simple to prove. It is proven in the text. It's an intuitive idea, which is helpful to us. One more thing in this section. The Betweenness theorem, which means it can be proven, and we should probably do that when we gather, but at least I'll give you a chance to take a look at it. So we're going to let A and B and C be on line L, and we're going to let f from L to the real numbers be a coordinate function for L. We say that C is between A and B if and only if f of C is between f of A and f of B. in increasing or decreasing order. It doesn't matter if it's in increasing or decreasing order. If f of c is between f of a and f of b, then we say that c is between a and b. This is one of those things that almost makes sense if you think about it. Just so you know, and to drive home everything you've learned in 239 Intro to Proof, if and only if means you've got to go both ways. So if we start with C being between A and B, then we have to use the coordinate function to establish the inequalities on the right side. Similarly, if we start with the coordinate function to use the inequalities on the right side, then we've got to be able to get to the fact that C is between A and B. Okay, that's a lot. That's a lot. But that's Venema's sections 3.1 and 3.2, and I'll do 3.3 in a moment.